Before we get into things today when it comes to the pumping lemma, I would like to talk a little bit about some aspects of the pumping lemma that have appeared in some discussions we may or may not have had in the past, but I would like to put everything together. So, just want to recap you where we are. It's a good idea. It's been a little while. So, we've talked about these things called regular languages. So what was our definition of a regular language? It was that it is a language for which there exists a deterministic finite automaton that recognizes it, right? There exists a deterministic finite automaton that recognizes it. That means that this machine, given all of the strings, any arbitrary set of strings on said alphabet, it is able to say accept for any one of the strings of that language and rejects all others. So another element of this I need to bring in is that we talked about Kleini's theorem, which is a characterization of the regular languages. Namely, we've also shown that I can take this part where I say DFA here, and when I say recognizes, I'm also going to include that it describes it. If you want to think about the DFA as a description of the language, you could replace this with a non-deterministic finite automaton. You could also replace this with an epsilon non-deterministic finite automaton. So this is where we have epsilon transitions or epsilon moves. So these are free moves I get to make without reading or consuming a symbol. And also we've talked about how we talked about regular expressions. And we've shown that you could describe a regular expression. Any regular language is described by a regular expression. We established this as a big part of Kleini's theorem. So just as a big picture, so keep in mind that's what the regular languages are. So what we're going to be doing is we're going to be establishing a property that all of these regular languages have. And it brings me back to talking about the deterministic finite automaton. So just want to remind you of how a DFA works. So I'm just going to draw the transition diagram of such a machine. So we're not going to go too terribly deep on this definition. I just want to remind you of the concept. So imagine I have a DFA with 3 states like this. This is just an example of one. So I have 3 states. We indicate this as the start state. Anyone I've put double lines around or double circled, those are final or accepting states. And of course, I have arrows. These are directed edges or arcs that take me from one state to another state on a symbol. So in this case, on the symbol 0, it transitions from Q0 to Q1. And of course, this is what my DFA is going to look like. So I have 3 states, and if I give you a string, for example, such as 0, 1, 0, what this machine will do with this string is it'll read symbol by symbol left to right. And on each, so it starts in the start state, here Q0. There's only one start state, just to be very clear, but there can be several final or accepting states. So I can go from this here to there upon reading the 0, right? It consumes the 0, the transition from Q0 to Q1. Then it reads the next symbol. It goes Q1 to Q1, so it stays in the same state. And then it reads the 0 and it goes to Q2. Now, this machine finished reading the input, so it accepts because it's in a final state upon completing reading the input. Is that clear, everybody? So please take note that to go from one state to another requires me to have a transition. And also, if I want to go and get accepted, I have to get to an accepting or final state. So all DFAs can be depicted using these transition diagrams. So the one thing I really want you to notice here is I can give you many, many strings. And I must stress that this DFA accepts a certain set of strings, a language. So the language here looks something like this. So do note that I can go 0. So if I give it a string such as this, 0, 0, notice it can go from, it goes Q0 to Q1, reads that. Q1 to Q2, it reads this, right? And it accepts that string. Do you notice that it can keep reading 1s and staying Q1 as long as the beginning and the end are 0, it can have 1s in the middle. So notice that this DFA so it accepts on strings of this form. 0, 1 to the n, 0 for any n greater or equal to 0. So it's allowed to have as many 1s as you want, 0 or more. So this set of strings, that's the regular, this is the language. And in fact, this DFA will correctly do that. I encourage you, if you're not convinced that this DFA is correct, to try sitting down and trying to prove it using some of the techniques we've seen in the past, such as state invariance. So this one has 3 states, so it makes it rather nice for applying the state invariant technique or argument that we had seen. Now, you might ask, why should I care about this at this point? So the ultimate question I would like to be able to address for you requires me to have a property that all regular languages have. Now, there's more than one way to characterize or give properties for regular languages, but the ultimate question I would like to answer is one that we asked some time ago. I'll rephrase it like this. Is every language regular? So in plain language, that means that if I give you any language, if this is the case, if it says yes, if the answer is yes to this, that means that I can always give you a deterministic finite automaton that recognizes that language. If the answer is no, that means that there's going to be some languages, perhaps many languages, for which I can never design a DFA for them, nor NFA, nor one of these, nor describe it with a regular expression. So we're going to ultimately answer this question once we've seen this property. So let me come back now to this, and I really want to emphasize something about the strings that get accepted by this DFA. There's specific kinds of strings that we're going to be interested in. So let's consider strings of this form. So consider strings W with length at least the number of states accepted by a DFA. You might ask, Dan, why would I consider that? Well, let's think about it. Let's think about this. And I want to come back to thinking about how this DFA executes as a walk or path. So when it reads each one of these, so last time when we talked about Kleini's theorem, we talked actually about how this path is like a set of it gives me instructions from going from one state to another state. It is a label for a walk or pathway. So for example, when I read off 0, 1, 0, notice it's just me following with my finger going 0, 1, 0. Now, you'll notice that the first example, unlike the second example I have there, the length of the string is at least the length the number of states, right? But let's think about that. what does that mean? What does that mean? So imagine I take this rope and I start right here. And I want to go from Q0 to Q2, which is the only final state in this DFA. And I ask you about string W in this circumstance. There's an interesting thing that might be popping up with strings of this length. So you imagine I want to go from Q0 to Q2 in this example. Remember, this is just an example. Does such a W repeat a state? That's a question I have for you. Does this W have to repeat a state? And the reason why I picked this example is because it's just a single, like notice that it's just, you go from Q0, Q1 to Q2, right? To get accepted, you have to go through this pathway at some point. But remember, DFAs may have multiple branching pathways where it may be the case there's multiple states. But remember, in terms of the execution of the DFA, it may as well just be examining one path. It may go through multiple states, but the point is if it gets accepted, it gets to some final state. So let's think about it. How many states are there here? There are 3 states. But if this length of my string is 3, how many transitions had to have occurred? How many transitions have to occur? So I go from Q0 to Q2. How many transitions have to occur to get to Q2, if that's the case? That's a good guess, but it's a little more than just that, right? Because remember, I have to go Q0, Q1, and then I have to go to Q2. So there's going to be at least 2 transitions that have to happen. But remember, the DFA works by reading one symbol at a time, right? It reads it left to right, and there's 3 symbols. So that means there's going to be how many transitions then? There's 3 symbols. It reads one after the other, and it follows the transitions on reading each symbol. So like we had here, we had 0, 1, 0. So how many transitions happen? It's 3. It's 3 transitions happen. But that's the thing. If there's 3 transitions and there's 3 states, let's answer this question. Does W repeat a state? So if I were to trace out the transitions. So for example, for this, what it looks like is this. Q0, Q1, Q1, Q2, right? So that's what it would look like. Because I go from Q1 to Q1, and then I go to Q2. So it means that the number of transitions that are happening is 3, right? But namely, notice that this equals the number of states, or it does repeat. Yeah, exactly. Yes, and there's a graph theoretic reason for this example. And this is something we talked about a little bit when we talked about graph theory in the past, is if I wanted to go from Q0 to Q2, if I think of this like a directed graph, if I have 3 transitions, that means the path is going to have to go to 3 different vertices. And I start here and I have to visit 3 vertices. I only have 2 more vertices, right? So there's not really any other options but to repeat one. So we would posit in this case that there exists a cycle in such a graph, if we think about the transition diagram as a graph. So there is a cycle that exists, namely it's this one right here on the so-called self loop, if we think about this in graph theoretic terms. So what would that look like then? So what is this going to look like? So for transitions for any such string, have 3 parts. So the first part are the transitions prior to. So now I'm going to give a name to this repeating state. We're going to call it, for our point of our discussion, PI. So in our example here, PI is always going to be Q1. So in this example, Q1 is PI. I should say to some PI, because keep in mind there could be multiple repeats. But I want to give a name to the one that for which it might repeat. In our example, it's always going to be Q1. But in other DFAs, it may not be. And then you have, of course, the transitions from PI through some transitions back to PI. So in our example, it just goes PI to PI, right? But it could be the case that there's multiple transitions that happen and then eventually comes back over here. Then the last part is the transitions from the last time PI is visited to a final state. So that's the structure of any one pathway or walk that I could take. So if imagine I'm walking from here to there to over there. Any such path has to look like this. And I picked this DFA specifically to make it easier for us to see this, right? So that's actually every one of the accepting paths. So a pathway that gets me to an accepting state, i.e. the string that I'm reading off dictates what this path will be. It always will have a form that looks like this, if the length of the string is at least the number of states. So that gives us an interesting idea here. If that's the case, if there's a repeat state, so a state I can keep going to, I can actually discover more strings that get accepted by the DFA as a consequence. So we can discover more strings accepted by the DFA by taking 2 0 or more times. Now you might ask, Dan, what do you mean by that? So let's think about strings that get accepted by the DFA. Well, we're already actually seen one right here. Do you notice that if I were to take this string, and you remember the path it takes is this? Do you notice that if I choose not to take the self loop, this exactly corresponds to this one right here, right? So that's just 0 0. So I can give you other strings that get accepted by this DFA, such as 0 0. We had 0 1 0, right? That's where you take the self loop once, because that's where we have the repeat state, right? But notice that I can actually keep continually using the repeat state in this example, but I must stress that it could generalize where it could be that you visit other states too, but come back to the repeat state. But the point is that the repeat state exists. So that means that also I can take that self loop twice. I can even take it 3 times. Miss Kitty, did you knock the string down? What a menace. And so on. But but we can exploit the fact that 2 exists to find more strings. And this brings us to a characterization for the regular languages. So this is so actually I should use the word characterization per se. It's a broader property that all regular languages satisfy. A characterization it has. So this brings us to what the pumping lemma is. So let's talk about what the pumping lemma is. Okay, Miss Katie? Yeah, you're being a little menace. Now you might ask, why is it called the pumping lemma? I'll give you an example in a moment. All it is just a phrasing of what we've talked about over here. So let me state the pumping lemma, and then I'll give you the intuition behind what we're doing over here, because I've actually just shown it to you up front. So let L be a regular language. Let L be a regular language. There exists constant P, and I must stress that this depends on L. And often this P, this constant, is called the pumping length. It's often called this. So there exists this constant P such that for all strings W that are in the language with length, so I'm going to denote the length like this, of the string W is at least this pumping length. String W can be rewritten like this, into 3 parts, X, Y, and Z. So to be a bit more precise about what I'm saying here, W can be dissected into 3 substrings. String W with this decomposition or dissection exists such that, or I'll say where, just because I'm going to have a lot of such that's coming up. It's going to sound like a little bit of a mouthful if you've never seen this before. Where the following is the case. 1, the Y part isn't going to be empty. So it's not the empty string. So that's the first thing. The second thing is that the length of xy, if I just consider x then y, the length of this string here cannot exceed p, the pumping length. And 3, the third property, is for every k greater or equal to 0, the string x, y to the k, z is in the language, L. This should kind of give you some alarm bells. You should feel like your ears are ringing, because something like this sounds awfully familiar, right? Because in our example here, I just showed you such a W, right? For that language. So do you notice how when in our example we had it where this Y part relates to that self loop and revisiting it over and over again, right? But here's the point I'm getting at. We're going to have it where there exists this string W so just to be very clear, for all strings W with this length, you can decompose it like this into, so it has these 3 properties. as we discussed over here. So let me give you the ideas just in plain language, just to summarize everything we've said, because I want to make sure you understand what the pumping lemma is. Here's the idea. So for any string, W in the language, where the length of the string is at least this pumping length, I'll say there is always a non-empty string y near the beginning of W that can be pumped. That is, one can repeat y0 or more times, 0 more times, the resulting string is in the language L. That's the idea of the pumping lemma. So we actually seen an example over here, and my example will help give you an intuition once we see the proof of the pumping lemma, what the pumping length might be. And you might ask, Dan, why is it called this? We say that it's pumping it. We're pumping y. So it's just like I'm going pump, pump, pump. So I can pump up the string like this by repeating that y part. So that's what we're referring to when we talk about the pumping lemma, is that it shows that there's going to be a way I can always come up with more strings for the language, namely by pumping y.